Kernels, networks, topologies, and graphs. So let's review similarity kernels. Suppose k of xy is the similarity of vector x to vector y in Rn. Then k of xy is less than or equal to 1 and is equal to 1 only if x and y are identical. And the similarity kernel is symmetric. If k1 and k2 are both similarity kernels on vector space Rn, then if alpha plus beta is 1 and alpha and beta non-negative, then alpha k1 plus beta k2 is also a kernel. This is what's known as a convex combination. The product is also a kernel, and there are other procedures for producing kernels. And then kernels lead to nearest neighbor methods. And similarity kernels lead to networks or graphs. In particular, suppose we have a set of training data, T1 to Tm, a subset of Rn. Then we can create an affinity matrix out of the evaluations on the Ti-Tj pairs from the training data. Notice we get a symmetric M by N matrix, symmetric because the kernel is symmetric. On the diagonal, it's all evaluations at T1, T1, T2, T2, so on and so forth, so the diagonal is equal to 1. Now we can do what's called thresholding, where we set all the coefficients to 0 that are less than some capital T greater than 0, something like that. This actually preserves the symmetry of the affinity matrix. Or we could use a K and N method. All but the highest K coefficients in each row are set to 0. Something like this. That actually could produce a non-symmetric matrix. And we want to use adjacency matrices, and this is where the diagonal is set equal to 0, and the kernel evaluations are weights, and then the strict adjacency matrix is where everything that's non-zero is set equal to 1. So let's look at an example. Suppose we have this affinity matrix of kernel evaluations and a threshold of 0.75. Then those coefficients below 0.75 are set equal to 0. So let me show you that again. Here they are, and below 0.75 set equal to 0. We set the diagonal equal to 0 to get an adjacency matrix. And then that defines connections between the training values as observations. And this is a weighted adjacency matrix where the edge weights are given by the coefficients of A. Now we can use a K nearest neighbors method where K is equal to 2. Same affinity matrix. We keep the 2 highest in the first row, then we keep the 2 highest in the second row. Notice we've actually broken symmetry. And continuing, we end up with a K nearest neighbors affinity matrix. And we put zeros on the diagonal, and that gives us a weighted adjacency matrix, and we replace all the non-zeros by 1, and we get the adjacency matrix for, in this case, a directed graph, because where we have broken the symmetry, we have a direction on that edge, as you can see here. For example, the California housing data, we're just going to look at the spatial features, latitude and longitude, and notice that gives us, for k equals 2 neighbors, a graph that looks like this, and for k equals 5 neighbors, a graph that looks like this. Now these are simple networks, and you can have large graphs that are not complex. This is also simple, these grid graphs. So what does it mean to be a simple network? It means it has a simple topology. The genus of a graph is the surface with the lowest genus on which the graph can be drawn without edges crossing. So planar graphs can be drawn in the plane without any edges crossing. This is certainly planar. And notice that we can put that on a sphere which has genus 0, no holes, and so therefore a planar graph has genus 0. This graph below can be redrawn, as you see here, and so it's actually also planar, no edges crossing. Similarly, this graph is planar, but I'll let you figure out why. A torus graph can be drawn on a torus, but not on a sphere. Now to see that this is actually a torus graph, let's redraw the graph. So here I've redrawn the graph, and now I can redraw it. But notice that this would be drawn on a torus without the edges crossing, but it's not planar. So it has a genus of 1. Now these are real-world networks, large order, with a very complex structure, a very high genus as a model of a topology. But nearest neighbor networks rarely model real-world networks. And this is the goal of this video, to show you this. In nearest neighbor networks, kernels are relatively simple and topologies are seldom complex. So real-world networks tend to grow. So the degree of a vertex in a graph G, denoted D of E, is the size of its neighborhood N of G of E. Often in real-world networks, the larger the degree of a vertex, the faster it tends to add neighbors. The rich get richer. A few of the many vertices, therefore, will develop very high degree. But most vertices start and tend to stay at a low degree even as the network grows. So this means the degree distribution of a graph is a function count of D. D is the degree as an independent variable, and the count's the number of vertices that have that degree. So here we have the degree distribution where we have nearly 7,000 that have degree 1, but only about 1,000 that have degree 5. So in particular, here's the specific: 7,000 with degree 1, 4,500 with degree 2, so on and so forth, 1,000 with degree 5. A scale-free network is a degree distribution that you often see in real-world networks. They tend to have many vertices with lower degrees, like you see here, and relatively few with higher degrees. And a graph is scale-free if its degree distribution is a power law, or at least asymptotically is a power law. So what do I mean by power law? I mean the count as a function of D is C times D to the negative P power. C is constant and P is constant. So something that looks like that. So power law distribution is a function, and therefore we want to look at it with points instead of bars because we're interested in the graph of this function. And if we take logarithms on both sides, then properties of logarithms tells us we get log count D equals log K minus P log D. And that means we get a straight line. In particular, Y is the log of count D equals B, the constant, is the log K, minus P is the slope, times X, which is the log D. In other words, the log-log plot of a power law is a straight line. Notice that our axes are in powers of 10, and our function, therefore, looks like a straight line in this log-log scale. The total count is the sum of all the counts, but we tend to divide the count function by the total counts, and we get a distribution P of D. P of D is the relative frequency instead of the actual counts. So we get a scale that looks more like that. So P of D is approximately the probability that a vertex V chosen at random will have degree D. And real-world graphs are often scale-free. So here's an airline network, and look at its power law distribution in log-log scale. It's almost perfectly a straight line. Here are some metabolic networks and gene regulatory networks in nature. Here is the log-log plot for archaea, bacteria, and eukaryotes. And approximately these are power law distributions. They're straight lines in log-log plot. So gene regulatory networks, the red dotted lines are the straight lines in the log-log plot. So yeah, approximately scale-free. But nearest neighbor graphs are more like random graphs, which are not scale-free. So what is a random graph? Well, an Erdős-Rényi random graph, G and P, has n vertices, and we're assuming here n is very large. And for any two vertices chosen at random, there's a probability P that those two vertices are adjacent. The average vertex degree which is bracket k, is therefore p times n. And that means we get distributions that look like this. And k and n graphs tend to be random-like rather than scale-free, and similar for threshold-defined graphs. If p is small, then the random graph tends to be disconnected with many components. If it's larger, it's an exponential graph. The degree is Poisson distributed for large n. And that is what we see when we look at k nearest neighbors. For example, remember our California housing, we had k equals 5, latitude and longitude, nearest neighbors graph. Here's its in-degree histogram. The out-degrees are all 5, and this is definitely not a power law distribution. And if we look at the log-log plot, that's not a power law distribution. If we look at the descriptive features instead of latitude and longitude, so this is non-spatial data, then our in-degree histogram, once again, it's not a power law distribution. And here you can see, definitely not a power law distribution. Power law distributions look like that in log-log scale. So real-world networks also tend to be small world, highly clustered with short distances between vertices on average. So to see what I mean by small world, let's first look at the clustering coefficient. Let V be a vertex in a graph G. The clustering coefficient is the number of pairs of adjacent neighbors over the number of pairs of neighbors. And it's defined for an individual vertex V. For example, here's a regular graph. All vertices have the same degree. Here's k equals 4. Let's pick out this vertex, and let's pick out this set of neighbors with this vertex V. Then here are the possible pairs of neighbors. So we're dividing by 6. There's 6 possible pairs. And notice that 1 and 2 are adjacent, and 2 and 3 are adjacent. So the clustering coefficient here is 2, 6. So let's go to another example. Let's pick this vertex out, and let's pull this vertex out with its neighbors. It has 7 neighbors. And so therefore, the pairs of neighbors corresponds to this 21 pairs of vertices. And notice there's only one adjacency among the neighbors of V, so the clustering coefficient is 1 over 21. The clustering coefficient can also be interpreted as the subgraph corresponding to V in its neighborhood as the number of actual triangles over the number of possible triangles. Each has to contain V. So here is a V and its neighborhood. There are 2 actual triangles, and there are 6 possible triangles. Likewise, there's 1 triangle, but there were 21 possible triangles. Here, there are no triangles, so this clustering coefficient of V is 0. Now, the clustering coefficient of an entire graph is just the average of the clustering coefficients of its vertices. So that means the clustering coefficient of a graph is between 0 and 1. If it's approximately 1, the graph is highly clustered on average. If it's close to 0, the graph is not highly clustered on average. Now let's go back to our Erdős-Rényi graphs. The average degree of a vertex is this bracket k, which is Pn. The clustering coefficient is actually just the probability, which is k over n, which is approximately 0, because remember, n here is incredibly large. And so that means much less than, that's notation. So the clustering coefficient of a random graph is close to 0. Now let's look at the shortest path length, or simply path length, between 2 vertices. So here's a path of length 4 from U to V, and here's one of length 4. But there's one of length 7, but there's one that's actually length 3. So this is the shortest path length, or path length from U to V, the shortest. So we let DUV denote the path length, the shortest path length between U and V. The average path length is just the average over all pairs of vertices of the path lengths. So for instance, here we have these path lengths, and the average is 4/3. Here we have these path lengths, and the average is 5/3. And I'll let you figure out the pattern. That's homework. Here's a triangle. It's got an average path length of 1, average path length of 2, average path length of 3. And I'll let you think about this one. Notice the average path length is greater than or equal to 1, and it can at times be huge. So the small world phenomena is many real-world graphs, G on average, are highly clustered and tend to have short path lengths on average. That's just sometimes called the 6 degrees of separation. A graph is small world rigorously if both the clustering coefficient is approximately 1 and the average path length is also approximately 1. High clustering, short distances. An airline network is small world. Notice it's highly clustered because most of the flights out go through only a few hubs. Gene regulatory networks, the smaller L of G is, the more quickly a cell can modify its activity. The larger the clustering coefficient, the more robust is the cellular response to various stimuli. Facebook, there are about 1 billion Facebook users in 2019, about 70 billion friendship links or edges, Twitter similar. The average shortest path length in 2019 in Facebook was 4. That means you and a randomly chosen other user could be living in China. A friend of your friend knows a friend of their friend. You've got a friend, they've got a friend, and they have a friend in common. 4 degrees of separation. So high clustering coefficient is due to the existence of communities. A community is a highly connected hub, like we saw in the airline network. Communities tend to attract members of other communities, forming even bigger communities. But the graphs produced by algorithms for k-nearest neighbors, for clustering and so on, are rarely small world or scale-free. So complex networks in the real world tend to be scale-free that grow by adding edges much faster than they add vertices. They have communities of communities of communities while maintaining low average path length. So this is not a community of communities, and look how long it takes for you to go from vertex U to vertex V. This is a large path length on average. So this is not real world. Real world is communities of communities of communities. Notice this community of communities has all the distances are less than or equal to 3 between any two vertices. But K and N graphs tend to be more like random graphs. So K nearest neighbor graphs are very useful and widely used, but they usually are only a superficial approximation of the complex topology of a set of big data. They often are not complex. They are neither small world nor scale free. But real world networks tend to be complex networks that are small world and scale free. So caution. Nearest neighbors are very useful, but they're not real world models of real world complex network structures.